Light is everywhere. Right now, it is pouring through your window, bouncing off this screen, entering your eyes at 300,000 kilometers per second. You have spent your entire life surrounded by it, moving through it, seeing the world because of it. And not a single physicist alive today can tell you what it actually is. Not in a way that makes complete sense. Not without a contradiction hiding somewhere in the explanation. The strange truth is this. Light behaves like a wave when you aren't watching it closely. The moment you try to catch it, it behaves like a particle. It travels through the vacuum of space with nothing to travel through. It takes every possible path from one point to another simultaneously, and then somehow arrives in exactly one place. It has no mass, yet it carries momentum. It moves at a speed that no clock can measure from the inside, because for light, time does not pass.
For 300 years, the smartest people who ever lived tried to answer one question. What is light, really? Every single time they thought they had it, Newton, Maxwell, Planck, Einstein, reality came back and told them they were wrong, or at least not entirely right. The story of light is the story of science at its most honest, building towers of certainty, watching them fall, and discovering that the rubble contains something more interesting than the tower ever did. That pattern, certainty, collapse, deeper truth, is not just how we learned about light. It is what light, of all subjects, taught us about how truth in science actually works. That every answer is provisional. That the closer you look, the stranger and richer the picture becomes. That being wrong, precisely and carefully, is how you get less wrong. We are not at the end of that story. We are somewhere in the middle. And the middle, it turns out, is where all the interesting things happen. If the real strangeness of the physical world, told without mysticism, just the actual science, is the kind of thing you want more of, subscribing and hitting the like button right now makes sure you don't miss what comes next. Because what comes next is one of the wildest intellectual journeys in human history. Let's go back, way back, to a time before anyone had the tools to even ask the question properly. The ancient Greeks thought about light. They thought about everything, but their picture was backwards in a way that took centuries to correct. Several of the most influential Greek thinkers believed that vision worked through emission. The eye in this model was an active thing. It sent out visual rays, invisible feelers that reached outward and touched the objects you were looking at. That was how you saw. Euclid, working around 300 BCE, built an entire geometry of vision on this assumption. His optical treatise survives. It is mathematically rigorous. It is also inside out. The light, in Euclid's picture, was coming from you, not to you. Aristotle pushed back against this, arguing that the eye could not possibly emit anything fast enough to account for the instant appearance of stars when you open your eyes at night. If seeing required you to send something out across the cosmos, why would the stars appear the moment your eyes opened? Something was wrong with the emission model. But Aristotle's alternative, that color and light were qualities transmitted through a transparent medium, was only slightly less confused. The Greeks were brilliant at asking questions. They had almost no way to test the answers. What they did establish, and what would survive every revolution in physics that followed, was one basic geometric fact. Light travels in straight lines. You can see this in how shadows work, in how light comes through a small hole and projects an image on the opposite wall. Euclid had the geometry right. The physics underneath it was completely unknown. Fast forward 1500 years. By the time of the Islamic Golden Age, scholars in the tradition of Ibn al-Haytham, who in the early 11th century wrote his Book of Optics, had already corrected the Greek error. Al-Haytham demonstrated, through careful experiment and argument, that light enters the eye from external objects. Vision is passive. The eye receives. This was a genuinely massive conceptual shift, and it happened centuries before European science caught up with it. Al-Haytham also studied refraction, the bending of light when it passes from one medium to another, and he studied what happens when light passes through small apertures. The pinhole camera, the camera obscura, was understood as a physical phenomenon, not a trick. Even with these advances, the deeper question remained completely open. Light bent when it entered water. Light reflected from mirrors. Light produced colors through prisms. All of these were observable facts. None of them told you what light was. Then came the 17th century. Two very different men arrived at two very different answers. The fight between them would define physics for the next 200 years. Christian Huygens was a Dutch mathematician and physicist, working in the second half of the 17th century, convinced that light was a wave. Not a wave in water or air, something more subtle. A wave propagating through a medium that permeated all of space, which he called the ether. His reasoning was elegant. Waves from different sources can pass through each other without destroying each other. You can see two candles across a room simultaneously. If light were made of particles, particles from different sources would collide. Waves overlap and pass through. This had to be waves. In 1690, Huygens published his treatise on light. It contained a genuinely brilliant insight about how waves propagate. The idea that every point on a wavefront acts as a source of new, smaller waves, and that the combined effect of all these secondary waves produces the advancing wavefront. This principle still carries his name. Huygens built an entire wave-based theory of reflection and refraction that gave the right mathematical answers. The problem was Isaac Newton. Newton had been experimenting with light for decades. His famous prism experiments in the 1660s, conducted during the plague years when Cambridge had sent everyone home and Newton had retreated to his family estate at Woolsthorpe, showed that white light was not a single pure thing. Pass it through a prism and it spreads into a spectrum. Pass the spectrum through a second prism, pointed the other way, and the colors recombine into white. Newton interpreted this as evidence that light was made of different kinds of particles of different sizes, each producing a different color sensation. Smaller particles blue, larger particles red. The prism wasn't changing the light, it was sorting it. Newton published his Optics in 1704. Unlike his Principia, which was written in dense mathematical Latin and accessible only to specialists, the Optics was in English, readable, full of described experiments. It became enormously popular. Newton had already given the world his laws of motion and gravity. His authority was, at this point, almost supernatural. When Newton said light was particles, most of the scientific world believed him. Newton had arguments. His corpuscle theory explained reflection cleanly. Particles bounce off surfaces the way billiard balls do. It explained the straight-line propagation of light, which seemed far more natural for particles than for waves. If light were waves, like sound, it should bend around corners. Sound bends around corners. You can hear someone shouting from behind a building even when you can't see them. Light does not bend around corners. This seemed to Newton and his contemporaries like decisive evidence against the wave picture. There was one awkward fact that Newton struggled with. He had himself observed what we now call Newton's rings, an interference pattern visible when a curved glass surface rests on a flat one, producing concentric circles of color. Newton explained these with an elaborate theory of fits, the idea that light particles could alternate between dispositions to reflect or to transmit. It was, charitably speaking, complicated. His wave rival Huygens had died in 1695, before Newton's Optics was even published. He could not fight back. His wave theory sat neglected for almost exactly a century, overshadowed by the weight of Newton's reputation. The 18th century was Newton's century. Corpuscles, particles, light fired in straight lines from sources to eyes. The picture was confident. The picture was complete. The picture was not quite wrong, just incomplete in ways nobody could yet see. The man who cracked it open was a physician. Thomas Young was born in 1773 in Somerset, England, and from childhood he was extravagantly gifted. He could read by the age of 2. By 14, he had studied Latin, Greek, French, Italian, Hebrew, and several other languages. He went on to become a medical doctor and a practicing physician for most of his adult life. He was also a physicist, a physiologist, an Egyptologist, one of the people who worked to decipher the Rosetta Stone, and he held firm opinions about musical theory. He was called, not entirely ironically, Phenomenon Young. In the late 1790s, Young turned his attention to light. He had been studying the physics of sound, which behaves as a wave, and he noticed that many mathematical descriptions of sound waves could be applied to light. What struck him was Newton's rings, those concentric circles of color that Newton himself had observed and struggled to explain. Young looked at them and thought, this is what happens when waves overlap. When two waves of the same frequency arrive at the same point slightly out of step with each other, they either reinforce or cancel, bright and dark, exactly like the rings. But thinking something is not proving it. Young needed an experiment. In 1801, he allowed sunlight to enter a darkened room through a small hole in a window shutter, creating a narrow beam. He then placed a thin card. He gives the width in his later published paper as approximately 0.85 millimeters in that beam of light, edge on, splitting the beam in two. He observed the shadow region behind the card. Where any particle theory predicted a dark zone with sharp edges, he saw fringes, alternating bands of light and dark. The light from the two sides of the card was interfering with itself. He covered one side of the card. The fringes disappeared. This was the critical result. The fringes were not caused by the card bending the light. They were caused by the two beams combining. When only one beam was present, there was nothing to combine with, and the pattern vanished. This only made sense if light was a wave, two wave trains overlapping, sometimes adding to brightness, sometimes canceling to darkness. Young presented this work to the Royal Society in 1801 and published it more fully in 1804 in a paper called Experiments and Calculations Relative to Physical Optics. The reaction from the British scientific establishment was cold. The Edinburgh Review, not a scientific journal but a literary and political magazine with enormous influence, published an anonymous attack that was withering and personal. The author turned out to be a Scottish lawyer named Henry Brougham, not a physicist, and he accused Young of being obscure, confused, and producing work of no practical value whatsoever. Young was angry. He wrote a pamphlet defending his experiments in precise detail and offered to sell it at cost price. He sold exactly one copy. Pause here for a moment, because this is not just a story about light. This is a story about what happens to truth when it conflicts with established authority. One of the most important experiments in the history of physics, an experiment that directly contradicted the most prestigious scientific theory of the age, was publicly mocked and essentially dismissed, not by ignorant people, by educated people who were so certain Newton was right that they could not properly look at what Young had shown them. The authority of Newton was so complete that direct experimental evidence against his theory could be published in the Proceedings of the Royal Society and still be waved away as confused nonsense. This is what makes the history of light so much more than a catalogue of discoveries. It is a record of how difficult it is for human beings, even brilliant ones, to revise what they already believe. The truth was on the table. Nobody wanted to look at it. Young himself was in some ways too far ahead of the available mathematics. He could show the fringes. He could argue they were interference, but without a complete quantitative theory, critics could always claim his reasoning was suggestive rather than decisive. That maturity came from France. In the first decade of the 19th century, Augustin Jean Fresnel, an engineer working for the French government who had taught himself the physics of waves, independently arrived at the same conclusion as Young. Fresnel went further. He developed a rigorous mathematical theory of wave optics that could predict, quantitatively, how light would behave when it passed through apertures, around obstacles, through multiple slits. Fresnel submitted his wave theory to the French Academy of Sciences in 1818 as a prize essay. One of the judges was Simeon Denis Poisson, a committed supporter of the corpuscular theory. Reading Fresnel's mathematics, Poisson found what he believed was a fatal flaw. According to Fresnel's equations, if you placed a circular obstacle in a beam of light, the wave theory predicted a bright spot right in the center of the shadow behind it. Poisson thought he had destroyed Fresnel's theory with this reductio ad absurdum. Another judge, Dominique Arago, went and did the experiment. The bright spot was there, exactly where Fresnel's equations said it would be. The man who predicted the result as a joke got the result named after him. Poisson's spot remains one of the more ironic namings in scientific history. That result, around 1819, shifted opinion decisively. Add to this the measurement by Léon Foucault, the same Foucault of the pendulum, showing in 1851 that light travels slower in water than in air. The corpuscular theory predicted the opposite. The wave theory predicted correctly. Newton's particles were not just doubted now, they were wrong. Light was a wave. The only remaining question was, a wave of what? James Clerk Maxwell arrived at Marischal College in Aberdeen in 1856 as a 25-year-old professor, and he was already thinking about fields, not agricultural fields, the abstract mathematical kind. The idea that electric and magnetic forces didn't just act between objects directly, but spread through space, creating invisible structures of tension and influence. Michael Faraday had pictured these field lines visually, drawing them in his notebooks, seeing the patterns iron filings made around magnets. Faraday was not a mathematician. Maxwell was. He was determined to take Faraday's intuitions and turn them into rigorous equations. He had been working on electricity and magnetism for years, building and refining his mathematical framework, when in 1865 he published a paper called A Dynamical Theory of the Electromagnetic Field. The paper contained what we now call Maxwell's equations, 4 relationships that described how electric and magnetic fields are created, how they interact, how they change in time. But the equations did something else, something Maxwell had not fully anticipated. When he combined the equations for a changing electric field and a changing magnetic field, a wave equation fell out of the mathematics. Not a wave in water, not a wave in air, a wave where an oscillating electric field generates an oscillating magnetic field, which generates the next oscillating electric field. The two fields producing each other in an endless chain, propagating through space. Maxwell calculated the speed of this electromagnetic wave not from any light experiment, but from 2 constants measured in pure electrical work, measurements involving capacitors and magnets, nothing to do with optics at all. The number he derived was 310,000 kilometers per second. The speed of light, measured at that time, was approximately 315,000 kilometers per second. The agreement was, as Maxwell wrote with characteristic British understatement, so exact that we can scarcely avoid the inference that light is itself an electromagnetic disturbance. Think about what just happened. Maxwell was studying electricity. Light appeared in his equations, unasked for, at the right speed. The derivation was not approximate, not metaphorical. The number matched. Light was electricity and magnetism, oscillating together, carrying each other forward through empty space. Maxwell had unified electricity, magnetism, and optics, 3 separate branches of physics, into 4 equations. He had done it not by building experiments, but by sitting with mathematics and following where it led. When you hold a magnet near a wire and create a current, you are making a very slow version of the same phenomenon that carries starlight across the galaxy. Even Maxwell kept the ether. Even after showing that electromagnetic waves needed no mechanical medium to sustain them, he still pictured those fields as stresses and strains in the luminiferous ether. The physics allowed waves in nothing. The intuition resisted it. Think about what a wave is. Pick any wave you have ever encountered. Ripples spreading from a pebble in a pond, waves in water, sound across a room, pressure waves in air, a vibration along a guitar string, a wave in the string. Everywhere you look, a wave is a disturbance in something. For a physicist trained on Newton's mechanics and Euler's fluid dynamics, the idea of a wave with no medium to wave in was like asking what a flame looks like when there is no fire. The words refused to connect. So the ether was not a fringe idea. It was the mainstream, built out carefully, methodically, with calculated properties. The ether had to fill all of space uniformly. Otherwise, the speed of light would vary from place to place. It had to be perfectly transparent. Otherwise, light would scatter just traveling through vacuum. To transmit the transverse waves Maxwell's equations demanded, it had to behave as a solid. Liquids can only carry longitudinal waves, like sound.
The ether had to be a solid, and yet the Earth moved through it. The planets orbited the sun through it. Comets traveled billions of kilometers through it. None of them slowed down. The ether was a solid more rigid than steel that offered zero resistance to the motion of physical bodies.
It did exactly what was needed, and nothing inconvenient. Lord Kelvin, who was the dominant figure of late Victorian physics, spent years trying to build detailed mechanical models of how the ether could be rigid to electromagnetic waves, but transparent to matter. Vortex models, gyroscopic models, elaborate constructions of spinning fluid tubes. None worked. He kept trying. When Albert Michelson, a young American physicist, decided in the early 1880s to detect the Earth's motion through the ether, he was not doing something radical. He was trying to measure a quantity that everyone already believed existed. The logic was straightforward. If the Earth moves through the ether, there should be an ether wind. This wind should affect the speed of light, like a cyclist who feels a headwind on a calm day simply by moving forward. Light traveling with Earth's motion would be slightly slower relative to the Earth than light traveling perpendicular to it. Michelson's interferometer could detect this difference through changes in how two perpendicular light beams interfered. After an unsatisfying preliminary attempt in Berlin in 1881, Michelson rebuilt his apparatus in 1887, working with chemist Edward Morley at what is now Case Western Reserve University in Cleveland, Ohio. The interferometer was mounted on a massive sandstone slab floating on liquid mercury in a circular iron trough, isolated from building vibrations. Light beams reflected back and forth by mirrors around the edges of the slab, covering 11 meters per arm. The whole apparatus rotated slowly, cycling the arms through different orientations relative to Earth's motion. They ran the experiment in July of 1887. They watched the interference fringes. They measured nothing. No shift, or more precisely, a shift so tiny, less than 1/40th of what the ether model predicted, that it was statistically indistinguishable from zero. Michelson was not jubilant. He was frustrated. He had set out to measure the ether wind, and his instrument had returned silence where a signal should have been. He wrote to the British physicist Lord Rayleigh that the result was decidedly negative and expressed disappointment. He would return to variations of the experiment for decades. The null result never changed. The physics community responded, for about a decade, with collective avoidance. Hendrik Lorentz proposed that physical objects actually contract slightly in the direction of their motion through the ether. The measurement arm of Michelson's interferometer would shorten by just the right amount to mask the ether wind, even if one existed. George Fitzgerald proposed the same thing independently. The Lorentz-Fitzgerald contraction was not a fundamental truth about space. It was a property attributed to matter, objects compressed by their passage through the ether. A somewhat desperate lifeline for a theory that was running out of road. The ether was dying. Nobody had announced it yet. By 1900, the condition of theoretical physics had a particular quality, triumphant on the surface, quietly fractured underneath. Maxwell's equations described electromagnetism with extraordinary precision. Newton's mechanics governed everything from billiard balls to planetary orbits. A Munich physics professor named Philipp von Joly reportedly told a student in the 1870s that physics was essentially finished. A few minor loose ends remained, but nothing of fundamental importance was left to discover. The attribution of similar sentiments to various figures of the era reflects something real about the period's mood, whoever first said it. The student, von Joly advised, ignored him, and went on to become one of the most important physicists of the 20th century. His name was Max Planck. By 1900, Planck was working on one of those so-called minor loose ends. His problem concerned blackbody radiation, how hot objects radiate energy across different wavelengths. The spectrum had been measured precisely. What was missing was a derivation, an explanation from first principles of why the spectrum had exactly this shape and not some other. Two formulas existed, both inadequate. A formula developed by Wilhelm Wien fit the high-frequency end beautifully, but collapsed at low frequencies. The formula derived from classical wave physics by Lord Rayleigh and James Jeans fit the low-frequency end, but predicted catastrophic results at high frequencies. It said a hot object should emit infinite energy in the ultraviolet range. This became known as the ultraviolet catastrophe, which captures the severity accurately. Classical physics, applied consistently, predicted that every warm object in the universe should be radiating infinite energy at all times. The universe was conspicuously failing to do this. Planck tried for years to derive the correct black-body spectrum from existing physics. In late October of 1900, at a meeting of the German Physical Society, he presented what he called an interpolation formula, a mathematical expression that fit the experimental data across the entire frequency range. He had found it not by deriving it from physical principles, but by constructing a formula that smoothly connected the two working partial formulas at the extremes. It worked perfectly. He had no idea why. Over the following weeks, working backward through the mathematics to understand what physical assumption his formula required, he found something he did not want to find. To make the derivation work, the energy of the oscillating atoms in the blackbody walls could only take certain discrete values, not continuous values. Not any amount you like, the way a ball rolling down a slope can have any speed. Only specific, evenly spaced steps, as if the energy came in chunks. The size of each chunk was proportional to the oscillation frequency, and the proportionality constant was a tiny new number that Planck called h, Planck's constant. He described it as a mathematical trick, a formal device, not a statement about physical reality. He did not believe energy actually came in discrete units. The idea violated everything in classical physics. Energy was continuous, had to be. Planck assumed he had found a computational convenience that some deeper, continuous theory would eventually explain. He spent, by his own later account, the better part of a decade searching for that deeper theory. He never found it. A 26-year-old patent clerk in Bern, Switzerland, read Planck's paper in 1905 and did something Planck himself had refused to do. He took it seriously. Albert Einstein had finished his physics degree at the ETH in Zurich and had failed to secure an academic position. He was working as a technical expert, third class at the Swiss Patent Office, evaluating applications for electromagnetic devices, reading physics in his spare time, publishing papers in the Annalen der Physik. In 1905, he published 4 papers, any one of which would have made a normal career. The one relevant here dealt with the photoelectric effect. The photoelectric effect had been observed in 1887, ironically the same year as Michelson-Morley. When ultraviolet light shines on a metal surface, the metal emits electrons. The strange part was how the emission depended on the light. Classical wave theory said the energy of a wave depends on its intensity, brightness. Brighter light should eject electrons with more energy. The experiments said otherwise. The energy of the emitted electrons depended only on the frequency of the light, not its brightness. Intense light at the wrong frequency ejected no electrons at all. Dim light at the right frequency ejected electrons immediately. Brightness affected only how many electrons emerged, not how energetic they were. A wave model had no explanation for this. Waves transfer energy continuously, and more intense waves transfer more. Frequency shouldn't matter, only amplitude. Einstein connected Planck's formula to the experimental data. If energy comes in chunks, if Planck's trick was not a trick but a truth about nature, then light itself must come in chunks, discrete packets, each one carrying exactly h times the frequency. Each packet could eject exactly 1 electron. The energy of the ejected electron would equal the packet's energy, minus whatever it cost to pull the electron free of the metal. Since packet energy depends only on frequency, electron energy depends only on frequency. Brightness just means more packets, so more electrons, but each one at the same energy. Einstein called these packets quanta. We now call them photons. Light was particles again, after everything. After Young's cardboard, after Fresnel's mathematics, after Poisson's spot, after Foucault's measurement, after Maxwell's equations. After all of that, the light that behaved so perfectly as a wave was, when you actually went to catch it, made of individual, discrete, localized packets. The two pictures that 2 centuries of physics had treated as mutually exclusive, wave or particle, you must choose, turned out to both be correct, simultaneously, depending entirely on what you were measuring. Planck himself refused to accept the photon for years. He was a member of the Nobel Committee when Einstein was belatedly awarded the Nobel Prize for the photoelectric effect. Einstein received the prize for 1921, with the announcement coming in 1922. And even then, many physicists considered the photon idea the most philosophically destabilizing aspect of Einstein's work. Planck had hoped quanta were a mathematical artifact. Einstein had insisted they were real. The experiments kept agreeing with Einstein. Something was broken in the foundations, not a crack to be patched. A fault line running through the entire structure. Light was a wave. The mathematics proved it. Light was a particle. The experiments proved that too. These statements were simultaneously true and logically incompatible within any framework classical physics could provide. And a generation of physicists, the most talented in the world, were about to spend 3 decades rebuilding those foundations from scratch. In 1909, Geoffrey Ingram Taylor, a 23-year-old Cambridge physicist, set up an experiment so simple it looked like an undergraduate demonstration. He took a light source, dimmed it so far down that only 1 photon was passing through the apparatus at a time, and shone it through a double slit onto a photographic plate. He left the plate to expose for 3 months. 3 months of single photons, one by one, going through the slits. When he developed the plate, there were interference fringes, the same alternating bands of light and dark that Young had seen more than a century earlier. The same pattern that proved light was a wave. Each photon had arrived alone. There was nothing for it to interfere with. No second photon, no overlapping beam, a single particle going through the apparatus by itself. And yet the pattern it built up, 1 dot at a time over 3 months, was the pattern of a wave, as if each particle somehow knew about both slits, as if it had traveled through both simultaneously, and arrived at a location dictated not by a straight line trajectory, but by wave mathematics. This is the moment that should break something in your picture of the world. Not as a rhetorical device, literally, because it is not a paradox that resolves cleanly on one side or the other. This experiment has been repeated with electrons, with neutrons, with entire atoms, with molecules containing 60 carbon atoms arranged in a sphere. Every time, the interference pattern. Every time, the individual particles arriving one by one, building up a wave picture. The universe is not choosing between wave and particle. The words wave and particle are our problem, not the universe's. Niels Bohr spent more time than almost anyone else staring into this particular abyss. He was not a man who rushed to easy answers. Bohr, who had built his model of the atom in Copenhagen in 1913, and who over the following 2 decades became the philosophical center of what would be called the Copenhagen interpretation of quantum mechanics, had a phrase he returned to repeatedly: complementarity. Wave and particle were complementary descriptions of the same reality. Neither one was the full picture. Neither one was wrong. They were like 2 projections of a 3-dimensional object onto 2 different flat surfaces. Each projection is real. Each gives genuine information, but neither one gives you the object itself. The object exists in a space you cannot directly see. Einstein was not comfortable with this. He spent the last 30 years of his life arguing that quantum mechanics was incomplete, that the probabilistic weirdness was a sign of missing information, not a fundamental feature of reality. At the Solvay conference in Brussels in 1927, the room contained more concentrated physics talent than perhaps any other gathering in history. Einstein, Bohr, Heisenberg, Schrödinger, Pauli, Dirac, de Broglie, Born, Planck, and the central argument was precisely about what quantum mechanics meant, whether it described reality itself or only our knowledge of reality. Einstein kept insisting that God does not play dice. Bohr reportedly told him to stop telling God what to do. The equations were not in dispute. The interpretation of the equations was a battle that lasted decades, and in one sense has never entirely ended.
So what is a photon, actually, when you try to pin it down? The answer that quantum electrodynamics, the theory developed primarily by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the late 1940s, gives you, is something that resists every familiar category. A photon is an excitation of a field. Picture the entire universe filled with an electromagnetic field, spread through every point of space at every moment of time. Not the ether. The ether was a mechanical substance, like a cosmic jelly. This field is more fundamental than any substance. It is not made of anything. It is not a property of anything. It is a feature of the vacuum itself, present even in what we would call empty space, especially in empty space. A photon is what happens when that field vibrates. When energy is added to the electromagnetic field in a localized way, the field develops a quantum of excitation. That quantum travels, spreads, evolves according to wave equations, and when it interacts with matter, it transfers its energy all at once, the way a particle would. The wave is real. The particle interaction is real. They are not two descriptions of two separate phenomena. They are two aspects of a single quantum field excitation. The wave describes probability, where the interaction might happen. The particle is the interaction itself. This is philosophically strange in a way that is easy to gloss over and important not to. The electromagnetic field, in this picture, is more real than the photons. Photons are events, moments when the field exchanges energy with matter. Between those events, asking where the photon is may simply be a malformed question, like asking where a wave is when nobody is measuring it. The photon has no mass, exactly zero. Every other thing that carries energy we encounter, a baseball, a sound wave, heat in a metal rod, is either made of massive particles or is a wave in something made of massive particles. The photon is a massless excitation of a field, carrying energy and momentum, with nothing contributing to a rest mass because it can never be at rest. The relationship between mass, energy, and momentum in special relativity is where this gets genuinely vertiginous. Massive objects at rest have energy. That is what E equals mc squared is saying. Massless objects cannot be at rest. The equations do not permit it. A massless particle that stopped would have zero energy and zero momentum. It would cease to exist. The photon moves at the speed of light not as an achievement, not as a limit it has strained to reach, but because any other speed is physically impossible for something without mass. It was created moving at light speed, and will move at light speed until it is absorbed, which is the closest thing it has to dying. Now the strangest part. From the photon's perspective, as a thought experiment, because the equations of special relativity make it impossible for any massive observer to actually ride along, no time passes. A photon emitted in the core of a distant star and absorbed by your retina after traveling 1,000,000 years has, from its own reference frame, experienced zero duration. The journey that took 1,000,000 years from our perspective took no time at all. The photon does not experience the universe between its creation and its destruction. It connects two events with no interval between them. This is what the mathematics of Lorentz transformations says when you push them to the limit of zero mass. For a photon, the space-time interval between emission and absorption is zero. Start and finish are, in the only sense that relativity allows us to call simultaneous, the same moment. The speed of light is not just the speed that light happens to move at. It is a structural constant of space-time itself, the conversion factor between space and time, the constant that makes them the same kind of thing in a four-dimensional framework. Einstein understood this in 1905. The constancy of light speed is built into the geometry of space and time. The reason nothing can travel faster than light is, at the deepest level, not an engineering problem. A massive object accelerating toward light speed encounters increasing resistance. The faster it goes, the more energy is needed to accelerate it further, in a curve that approaches infinity as the speed approaches light. You would need infinite energy to reach it. The ceiling is woven into the architecture of reality. This is not abstract. You use it every day. The GPS system in your phone
depends on an array of satellites carrying atomic clocks. Those clocks are moving relative to you at orbital speeds and are in a weaker gravitational field. Both effects, velocity through special relativity, gravitational field through general relativity, shift the rate at which those clocks run compared to clocks on Earth's surface. Without correction, the GPS clocks would drift by about 38 microseconds per day. Light travels about 11 kilometers in 38 microseconds. An uncorrected drift of 11 kilometers per day would make your GPS useless within hours. The corrections are built into every GPS receiver. Einstein's relativity is engineering for GPS. It runs in the background of ordinary life, invisibly, continuously. Step back even further. The light entering your eye is electromagnetic radiation at frequencies between roughly 400 and 700 terahertz. It has no color in itself. The electromagnetic wave at 550 terahertz, what you experience as green, is an oscillation of electric and magnetic fields at that frequency. The field does not know it is green. Green is something that happens in your visual cortex. The photoreceptors in your retina, 3 types of cone cells, each sensitive to a different frequency range, absorb photons and fire signals. Those signals travel through the optic nerve, are processed through multiple layers of neurons, and eventually produce the experience of color. The experience is generated by your brain, not received from the world. Consider what happens when the frequency shifts even slightly outside the range your cone cells cover. Ultraviolet light at 350 terahertz is physically just as real as green light at 550. It carries energy. It interacts with matter. It causes sunburn. You see nothing. Not darkness, nothing. Your brain receives no signal, so it constructs no experience. The light is there. You are simply absent from it. The mantis shrimp, which lives on coral reefs, has 16 types of photoreceptors compared to your 3. It detects wavelengths entirely invisible to you, including polarized light and a range of ultraviolet. It does not simply see more colors. It has access to dimensions of visual information that your nervous system cannot process at all. There is no experience you can have that corresponds to what a mantis shrimp sees, because you lack the hardware. The colors it perceives have no names in any human language. Same electromagnetic radiation, same photons, same field oscillations, experienced as vivid color by you, as something entirely different by a mantis shrimp, as nothing at all by organisms without photoreceptors. The color is not in the light. The color is what a particular nervous system constructs from light. What the universe contains is frequency. What you experience is an interpretation, your brain's rendering of frequency into something useful for survival, built by millions of years of evolution to be functional, not to be a faithful copy of physical reality. I find this one of the most disorienting facts in all of science. Not because it makes the world less real, but because it reveals how much of what feels most immediate, the blue of the sky, the gold of sunlight, the green of a forest, is a production. The world sends frequencies. The brain writes the experience. You have never seen light. You have seen what your brain does with it. And the surprises are not over. Right now, in facilities on 3 continents, experiments are underway that could force another revision in our understanding of light. The question of whether the photon has exactly 0 rest mass, not approximately 0, but precisely, mathematically 0, is still subject to experimental upper limits rather than absolute proof. Maxwell's equations demand exactly 0, but nature has a long history of not doing precisely what the equations demand. Current measurements put an upper bound on photon mass so small that it would have no measurable consequence for any physics we can currently test. But if that mass deviates from 0 by even the tiniest non-zero amount, Maxwell's equations are subtly wrong. Light would not travel at exactly the same speed at all frequencies. Over cosmological distances, that tiny frequency dependence would accumulate into a measurable dispersion. Gamma-ray bursts, the most energetic explosions in the universe, give us our longest ruler for this test. Photons from a single burst travel billions of light-years and arrive at our detectors within milliseconds of each other, across a huge frequency range. Each new measurement tightens the limit. consistent with exactly zero so far, but not proved. There are also ongoing questions about what happens to the concept of a photon near a black hole event horizon. The mathematics of quantum field theory and curved spacetime predicts that the vacuum itself radiates. This is the Hawking radiation prediction, that black holes should slowly emit photons due to quantum effects at their boundaries. As of today, Hawking radiation has never been directly observed. From any black hole we can currently study, it is too faint to detect. Analog experiments, sonic black holes in Bose-Einstein condensates in laboratory settings, have produced results consistent with the prediction. Whether a photon is well defined at the boundary of a black hole, where space-time itself is radically curved, remains an open question. And deeper still, the four fundamental forces of nature, electromagnetism, the strong nuclear force, the weak nuclear force, and gravity, are not unified in a single framework. The photon is the carrier of electromagnetism, described with extraordinary precision by quantum electrodynamics. Gravity is described by general relativity, also extraordinarily precise. At the scales where both quantum effects and gravitational effects are simultaneously important, billions of times smaller than a proton, we have no working theory. What a photon does at those scales, whether the concept of a photon even survives at those scales, nobody knows. 300 years. Newton's canon, Young's cardboard, Maxwell's equations, Michelson's mercury trough, Planck's reluctant formula, Einstein's patent office, Bohr's conference table, Feynman's diagrams. 300 years of the most talented minds in human history circling a single question. The answer they reached is this: light is a massless quantum excitation of the electromagnetic field, exhibiting wave-like propagation and particle-like interaction, traveling at a speed woven into the geometry of space-time, experienced by biological nervous systems as color through the machinery of perception. Its deepest behavior at the intersection of quantum mechanics and gravity, still unknown. That is not a comfortable answer. It contains, if you look at it directly, an honest acknowledgement that we are still somewhere in the story, not at its end. Each time physicists in the last 300 years thought they had closed the book, Newton's corpuscles, Fresnel's wave theory, Maxwell's fields, Bohr's complementarity, the universe opened another chapter. The pattern suggests that the next chapter is already being written in data from gamma-ray telescopes and Bose-Einstein condensate experiments and gravitational wave detectors. We just haven't read it yet. The photon that carried the image of a galaxy 12 billion light-years away into the James Webb Space Telescope left that galaxy when the universe was young, before Earth existed, before the Sun existed. It traveled for 12 billion years and ended its existence in a semiconductor detector that converted it into an electric charge that became a number in a data file that became an image on a screen. Zero time passed for the photon. All of human history passed for us. Something was moving through the universe before we were here to see it. Something carried information about the early cosmos across distances the mind cannot genuinely hold. We still cannot give you a complete account of what that something is. When you look at a candle tonight, a single flame radiating light in all directions, each photon leaving and spreading outward at the maximum speed reality permits, you are watching one of the most fundamental and least fully understood phenomena in physics. Not because we know nothing, because the more precisely we look, the more precisely we understand how deep the question goes. The physicists who spend their lives on this are not troubled by that depth. They are drawn to it. Because the persistent refusal of light to fit any single category, to be only one kind of thing, to submit to a single clean story, that is not a failure of understanding. It is the signature of a phenomenon that exists at a level more fundamental than the intuitions we were born with. Light was the first thing named in the oldest creation story we have written down. Let there be light, before the earth, before the sky, before anything that lives. And all this time later, we are still working out what we asked for. If that kind of honest, unresolved, endlessly surprising science is what you want more of, Real questions, real strangeness, no shortcuts. Subscribing and leaving a like helps more than you think. Every open question in physics is another video waiting to happen. And there are a great many open questions left.